Okay, let's continue our discussion about the analysis of the quicksort. And in the earlier video, I have already drawn something on my drawing board and showing you what is the possible worst case and the best cases. Okay, so well, for to answer this question, what will be the worst case of the algorithm? And then the answer is the partition is extremely unbalanced. It could be the majority or well, all the values are on one side, and then there's no value on the other side. So that's the worst case. And to answer the next question, what will be the best case of the algorithm? And we have also talked about that. Well, and that will happen when the partition is perfectly balanced. So we have 50 to 50% partition. And the next question, which is more likely to happen? Well, are we gonna have something more closer to the best case, or are we gonna have something closer to the worst case? And well, you may feel for the worst case, we have to go extreme. We have to be unlucky picking the largest value or the smallest value, and we have to do that more than once. We have to do that continuously. We have for each partition. Well, if for one partition we are unlucky, it doesn't matter because later we are going to have another partition. And the worst case happens when we always pick the largest value or always pick the smallest value among the values to be sorted. And this will be really, really unlucky, right? Well, but there is one exception. And the exception will be if we have a pre-sorted list already. And what is going to happen? Okay, so think about that. If we have already sorted a list low to high, and then what will be the first pivot? The first pivot will be the very first value, and the very first value happens to be the lowest value. So what do we have? We have a pivot which is smallest value, and then all the remaining of the values will be on the right side. Okay, so we didn't sort anything, but we know the pivot value, which is smallest value, we don't have to touch it anymore. And if we go the second round or the next recursion, and then what is the pivot? So the pivot will be the smallest value among the values to be sorted. So again, we pick the second smallest value, and then this is another worst case, and then we will have the worst case after the worst case after the worst case, and what we will end up with having the worst case in a sequence. So what do I mean is, say if we have, say, no, from 1, from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so if we want to sort this one, and then we pick this to be the pivot, okay, and then what is the partition? The partition will be on the left, there's nothing, right? And then the partition will be the partition. The pivot will be the pivot. And what will be the right part? The right part will be 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so this partition will be like this. So even though we have done a partition, and actually what we end up with is, well, for the left part, no value at all. And then the 1 is a pivot. So the pivot, we won't bother to touch the pivot anymore. And then we still have to sort the right half or the right sublist. And guess what? For the right sublist, we have n-1 values to be sorted. And that's not the worst thing. The worst thing is, what is the next pivot? The next pivot is 2. And so for the next partition, what is going to happen? Exactly the same thing. For the left part, there's nothing there. For the pivot is still the pivot, so the pivot is 2. And then all the remaining of the values will be on the right side, so we are going to have 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so this is the second partition. For the second partition, what do we have? We have the pivot, which is 2 at the right place, and then for the remaining of the values, they are on one side, and that's not the worst thing. The worst thing is the third pivot will be the smallest value to be sorted again. So we are going to continuously sorting the worst case until we go all the way to the end, and that is the worst case. So let's come back to the PowerPoint. Okay, so we have answered all the questions, and what is particularly the worst case? Well, worst case of the quicksort, and that is if we have a pre-sorted input. Okay, and then let's analyze the worst case. And actually, the worst case is very easy. Why? Because well, we know every time we are only reducing the problem size by 1, right? Say we used to have, our goal is we want to sort 10 values, and then after the first partition, and now our goal is we want to sort 9 values. So every time we can reduce the problem size by 1, but only 1. And the next one, our problem size got reduced by 1 again. So every round we reduce the problem size by 1, and that is the Tn equals Tn minus 1 and plus a big zeta. And what is the big zeta n? The big zeta n means there is linear cost. What is the linear cost? The linear cost is the partition itself, right? Remember, the partition is always a linear time algorithm. So every time we do one partition, and that will be the cost of a linear time. So, well, if you want to work on this with either substitution or iteration approach, and then you will find this is a zeta n square. So for the worst case, and we will have a zeta n square algorithm. Okay, and then what is the best case? The best case is also easy because, well, we are doing divide and conquer, and somehow we magically we are able to find the median every time when we do the partition. So every time we are dividing the problem size the problem into 2 n divided by 2 size of the problems. So that is Tn equals 2 Tn divided by 2, and again the zeta n, that is the cost of doing one partition. And for this one, you definitely want to use the master theorem to solve this, and then you will find this is a zeta n log n algorithm. Okay, so that's a very quick analysis of the best case and the worst case of the quicksort. And well, before we move on and talk more about the average case of the quicksort, and here is one question we can discuss. And how do we improve the quicksort? And for the quicksort, and one of the painful part is if the list is already sorted, and then we actually have to spend O n squared to sort it again. That's really painful. And how do we avoid that? And the number one thing is, well, the number one solution we talk about in the book is, well, we can randomize the input array. So when we have a array to be sorted, well, to avoid having a pre-sorted array, we shuffle those values anyhow before we send this data into the quicksort. And in this case, and we ain't gonna see the worst case. So that's okay. But what's the problem? The problem is we have to spend one extra cost to shuffle the list, right? And there is another way, that is to pick a random pivot element. And remember, in our implementation, we always pick the very first value. And the very first value actually causes the problem when the list is pre-sorted. So how do we pick a random value? And one of the approach is, well, instead of picking the very first value, we can pick one value at the beginning, one value at the end, and then one value in the middle. Okay, we pick 3 values, and then for those 3 values, we are gonna pick the middle one. and then this will guarantee that we will at least have some value on one side of the partition, and then we have some value on the other side of the partition. So we won't have a super bad partition. So this is one of the idea. And the other idea is, say if we have a random list, and then we just randomly grab one and then swap that value with the first one, and then we just continue with the approach we have talked before. However, for the very first value, since it has been swapped to a random value in the middle, and then we don't have to worry about the case that this list is pre-sorted. Okay, so by any means, when we add a few more lines of the code into the quicksort, we can avoid to have a quicksort runs for O(n) time on a pre-sorted list. Okay, so this is our goal. We want to avoid the worst case, and the worst case in the quicksort that is usually easily avoidable. Okay, so in this video, we analyze the worst case and the best case of the quicksort, and the next video we are going to continue to talk more about the average case. So for the quicksort, the worst case and the best case, they are easy. But for the average case, that's much harder. Okay, I will see you in the next video.